We all feel it, every single day. Time only moves one way, from the past through right now and into the future. It feels like the most basic rule of reality, right? But what if I told you that according to the fundamental laws of physics, this one-way street we're all on might be built on some seriously shaky ground? Today, we're going to dive into a pretty wild idea about the nature of time itself.
Okay, so let's just get right to the heart of it with this one question. On the most fundamental level, do the actual equations that describe our universe really care about the difference between the future and the past? The answer? Well, it's complicated. And it gets to the very core of why you can remember what you had for breakfast yesterday, but you have no idea what you're going to have tomorrow.
To even begin to answer that, we first have to talk about one of the most beautiful, most powerful ideas in all of science, symmetry. You see, physicists have this core belief that the deepest laws of nature should be elegant, they should be consistent, and they should be symmetrical.
Now, what does a physicist even mean by symmetry? It's basically the idea that if you change something, if you perform some kind of transformation, the underlying rules of the game stay exactly the same. So an experiment you do here should give you the same result if you did it on the other side of the galaxy, or 1 billion years from now. And there are a few of these really deep symmetries that we found. You've got charge symmetry, which is the idea that physics works the same if you swap a particle with its antimatter twin. Then there's parity symmetry, which says that if something can happen, its perfect mirror image should also be able to happen. And then finally, we get to the big one for today, time symmetry.
But here's where we hit our first little twist. When physicists talk about time symmetry, they're not just talking about one simple concept. They're actually talking about two totally different ideas.
On one hand, you have type 1, which we can call consistency. This is just the idea that the laws of physics don't change over time. Gravity works the same way today as it did yesterday. This one is pretty solid, we're all good with it. But then you have type 2, reversibility. And this is the really wild idea, that the laws of physics should work just as well if you ran the clock backwards. A planet orbiting a star would look just as physically correct in reverse as it does going forward. And this is the symmetry that's causing all the trouble.
Because that whole idea of perfect time reversibility, it turns out to be, as our source material calls it, pretty dubious. It's like there's a crack running right down the middle of that perfect mirror between the past and the future.
And that word from our source material is so important, dubious. It's not just saying time symmetry is wrong, it's saying it's suspicious. It's like the idea that time can just flow backwards as easily as forwards. It might look great in some clean, simple equations on a blackboard, but it just seems to fall apart when you look at the messy, real, complex universe we live in. So, here's the crucial point. This perfect forward/backward symmetry is sought to be very local. What that means is it might only really work as a good approximation for tiny, simple, and totally isolated systems. You know, like a couple of particles bouncing off each other in a perfect vacuum. But our universe, it's not small, and it's definitely not isolated.
And this brings us to the core argument for why this whole symmetry idea has to break down on the big scales. It's this beautiful, simple, yet totally profound idea. The universe isn't just a collection of separate things. It's one single, interconnected whole.
The entire argument really hinges on this one phrase. Just think about that for a second. If everything in the universe is woven from one single fabric, then anything that happens in one tiny corner has to, in some way, affect every other part. And this simple idea has a huge consequence. True isolation is impossible. So let's just walk through the logic there, step by step. 1. The universe is one interconnected fabric. 2. That means any local piece, you, me, this planet, anything, is constantly being influenced by everything else. 3. Therefore, no part of the universe is ever truly perfectly cut off from the rest. And 4. If all that's true, then this whole idea of a perfectly reversible local system is only ever an approximation that works for like a split second. The rest of the universe is always there tugging on it.
So what does this all mean? Well, it means the reason we experience an arrow of time, the reason it points so stubbornly from past to future, is because this perfect local symmetry is fundamentally broken.
And the conclusion is pretty stark. Because every single part of the universe is tied to the whole thing, we just can't turn time in reverse. It's impossible. To reverse one tiny little piece of the puzzle, you'd literally have to reverse the entire cosmic fabric that it's woven into.
And here it is, the final, absolutely mind-bending payoff. A lot of us have probably heard that time's arrow comes from thermodynamics. You know, the second law, the one that says things always get more disordered, entropy always increases. An egg can scramble, but it can't unscramble itself. But this argument, it flips that whole famous idea completely on its head. It suggests that entropy, that increase in disorder, isn't the cause of time zero at all. It's just a consequence of this much deeper truth, that the universe is one interconnected whole.
So we're left with this final, really provocative thought to chew on. If the past, the present, and the future are all just threads in one single cosmic fabric, does that mean the future is already, right now, pulling on the present? It's a thought that really challenges how we think about the flow of reality itself. Thanks for exploring it with us.